Okay, it's a kind of special talk because you will not learn new features of Java 21 or new feature of Hibernate 6 or I don't know, some agile feature you try to use next week. So everything I will tell you is something that you don't have to do yourself. It's done by some really nice guys, and they implemented it years ago, and you don't have to do anything to take part of this, what I will tell you. The JDK is optimized from release to release. So this okay. So the JDK is optimized from release to release to release. And optimized not in the way that new features are included, but optimized in a way that it's faster and it needs less memory. So that holds true for the whole JDK, but it's also true for strings, boring data type strings. Strings are special because all your applications will use so many strings that it will pay out if you invest in performance optimization in strings. That's for true. Okay, so what I will show you is something which is called intern strings. Probably you have heard of this. Eventually, you haven't heard of the third other points, compact and compressed strings, string deduplication, and indify string concatenation. So you introduced me, and it's true, I'm a professor at computer science. It turns out that I'm ein Schwabe, so I'm born in Metzing, not far away from here. And I study computer science at the University of Stuttgart, and then changed to northern Germany. So I'm also, I had the honor to be an expert group member of JSF 2.2 and JPA 2.1, and I have written some books about JSF, JPA, Hibernate, and eventually the older one will remember there was something called JBoss Theme, which was a predecessor of CDI. So, and I'm also here because I'm a JAG organizer of the JAG Ostfalen, which is located in Braunschweig. Okay, motivation. You are motivated, so we don't have to go into detail, but I will show you that we are not alone interested in strings. So there is a very good book by Scott Oakes, Java Performance, and there are some paragraphs in it named almost identical to the items I had on my slide. So you know where the ID comes from. And there is also a book called Optimizing Java from Benjamin Evans. It's not the DDD Evans, but another well-known guy, and Chris Newland, also very well-known. And there are also some paragraphs about strings in this book. There is a book, Quality Code, from Stephen Vance. It's only about testing, only how to write unit tests. And there is a complete chapter, string handling, in it. So strings are everywhere, and it's a nice idea to invest in strings. Okay, so before I will tell you something, please tell me something. So I will do a small quiz. And I will ask you, if you look inside a Java string, a single character is encoded with 1, 2, 4, 2 or 4, 1 to 4 bytes. And you're all Java developers, so don't be shy, raise your hands, and I will start. Who thinks a single character is encoded with 1 byte? Who thinks B, 2 bytes? Who thinks C, 4 bytes? Who thinks D, 2 or 4 bytes? And who thinks 1, 2 or 4 bytes? Okay, so the answer is not correct in general, but correct with some special Java version. And 2 bytes was correct till Java 5. Then to Java 9 it was D, 2 or 4 bytes. And since Java 9 it's E, 1, 2 or 4 bytes. Okay, so my first, and I will solve the quiz later on, and I will show you why it's as I told you. Okay, so Java is specified by 3 parts. There is a specification of the language itself, a specification of the virtual machine, and the complete Java doc also defines what your JDK is about. So there are 3 parts. And in the first part, the Java language specification, there is a paragraph 3.10.5 called string literals. And there is written that string literals are interned, so as to share unique instances. Unique instances means these strings are singletons, right? Unique instances means singletons. And I will tell you what constant expressions are in the example I will show you. And there's also a paragraph 12.5, creation of new classes. And there's written that if a class file is loaded into the VM, then all string literals in this class file are, first there's a lookup, are they already interned and are the singleton is already in some data structure? If yes, then use it. If not, insert this string literal from bytecode to this data structure. And the string concatenation operator plus, I will talk about it some later time. Okay, so these slides are not so nice to read for you, so I will sum up. Intern strings are stored in a so-called string memory pool. And when the class gets loaded into the VM, it is checked if the string is already in the pool. If so, use it. If not, insert it. And this is written in the spec, but it's also written in the Java doc of string intern, of the intern method. There is an intern method which does the algorithm I told you a minute ago. Okay, let's go into some code. So I've written some unit tests, and this will, of course, run green, 7 tests at all. And so these are 2 string literals, and they are of course equals, but they are also same. Assert same means they are same. No, usually you're used to use equals, but assert same means they are same. They are even same if variables referencing these literals, because these 2 hello world literals are inside the JVM a singleton. It exists only one time in the JVM hello world. So what are literal constants? What are constant literal expressions? Something concatenated by the plus sign. And even if you're doing some special concatenation or some different concatenation, These two strings, or these 5 strings, are concatenated to 2 strings. Both are hello world, and they are inside the JVM one singleton. So they are same. So if you are using string variables, as we seen before, they are also interned. But if you form an expression with variables, it's not a constant expression, but it's a variable expression, they are not same. So there are 2 instances of this. You can get the former result if you define them final. Then string 1 and string 2 are constants, constant literals, and this is a constant expression. So if you do some screenshots, it's okay, of course, but at the end you will, I will have a slide with QR code and a GitHub repository, so you can download all the examples here. Okay, so you remember the intern method. So as we have seen, these variable expressions are not same. But if you intern them, they are same. So the intern method checks it and, if necessary, puts them into this data structure. Okay. So, and if you call the constructor, all constructor strings are always do always exist on the heap, so they are never get interned. So if you are using new string or another constructor, string constructor is overloaded many times, so they will result in heap references. Okay, go ahead. So now we know that strings can be interned, and if they are interned, we can, so one can have the idea to not use equals, but to use the equal operator, equal, equal. So this is, in general, not a very good idea. Scott Oakes from the first book tells us that this is not really a good idea, it's a myth. The first reason is equals is implemented pretty fast. And the second reason is you have to intern. And the interning needs some computation. So you have to invest some time to intern them. And in many cases, it's not really a good idea to use this intern method and change from equals comparison to equal comparison. So maybe there are some cases where the interning takes some sense, but in general, probably you will not do it. Okay, now we know what string interning is and that these string literals are singletons. But we don't know how are they implemented. And they are implemented in a hash table, but not in a Java hash table. The hash table belongs to the virtual machine, so it's implemented in C++. And C is not as flexible as Java is. So we are used to use collections which grow if we put more input into them. So this C implemented hash table does not grow. So you have to think about a size which should be as great as the application has to use it. So one parameter of hash table is the bucket size. The bucket size is where the hash values are represented to point to the real instances. So the bucket size was 1009 till Java 7. Then they increased it to 60,013. And these two values are prime numbers. So you can read that a good bucket size has to be prime. So since Java 11, it's 65,536, which is not prime, of course. So don't ask me why, it's like it is. Okay, so is someone using Java 6 and older? So the older one will remember there was a movement in Java 7, so the permanent generation was moved to the meta space. And so if your hash table fills up with Java 7 and older, you get an out-of-memory exception perm generation, and if you are using 7 or newer, you get a heap space out-of-memory error. So if you want to optimize something with this hash table, first you have to convince yourself that you're using many, many strings in your application. So there is a JMap application inside the JDK, and you can use the -heap parameter and the process ID, and JMap will show you how many instances you're using. And after the program exits, the program will print out table statistics if you use the parameter print string table statistics. And if you are convinced that you should lower or increase your bucket size, you can do it with an option string table size equals, and then you have to use your prime or not prime number. Okay. So if I'm working on this talk, I have to do some research, and I'm convinced that all of the OpenJDK guys are really, really smart guys, really talented, intelligent, super developers, but eventually they are humans, and all humans make errors, as we all also do. So this is source code from the JDK. Also the comments are source code from the JDK. And in former times, in the string class, there were two fields, two variables, offset and count. And if you, for example, are using substring, the substring was allocated as a string instance, and the array holding the characters for the string was not allocated. So it points to the origin string. But offset and count was adjusted so that the substring was correct. So this is, on a first look, it's a good idea. On a second look, it's not so a good idea because it's a memory leak. So if you don't use the original string, you only use the substring, the original string can't be garbage collected because the substring still uses the array of characters. So this was a JDK issue. They can read the number, and if it's so in German it's magenta. I don't know the color in English. If it's kind of magenta, it's a link into the internet, and you can also download the slides from GitHub, and you can read about this issue. So offset and count was removed with Java 7. So now if you're using the string class, these two variables are never not inside the source code, and of course the class code. Okay, this singleton feature of strings was built into Java since Java 1.0. What I will show you now are three so-called JEPs, Java Enhancement Proposal or JDK Enhancement Proposal, and the first one is compact string. So the older one will remember something called applets. And because Java was invented in 1995, it was invented as an internet language, where they created the applets. And so it was the first the first language, to my knowledge, using Unicode and not trivial ASCII. So they decided to use, for the jar data type, 16-bit to encode. So this is also real Java source code. Inside the class string, there is a value field, a value variable, which is an array of jars. With Java 5, it was decided that Unicode 4.0 should be used to encode characters in Java. And Unicode 4.0 has some code planes which doesn't fit into 16 bits. So you have to use 32 bits. So it's a problem. You can enlarge the character data type from 2 to 4 bytes. But in Java, this is not a good idea. So so compatibility in Java is one of the most important features. So it was decided not to enlarge the jar data type. What they did is they defined so-called supplementary characters. And you can read in detail in the class Java character the details about supplementary characters. So they decided to use 2 jars for 1 character in those character encodings using 32 bits. So probably all of you are, so if I look at the faces, all of you don't use 32 Unicode encodings, probably? Okay. So it was done. And for example, there are slightly changes. In Java 5 and before, the length Java doc told us that the length is equal to the number of 16-bit Unicode characters. And in Java 6 and greater, it reads the length is equal to the number of Unicode code units in this string. So now we have, in general, strings represented with 2 bytes per character, and from time to time there is a character which is encoded with 2 jars, not with 1 jar, but with 2 jars. So not in 2 bytes, but in 4 bytes. But German, English, Spain, Italy, French, all fits into an ASCII number in the Legend 1 character encoding into 8 bits. So 1 byte suffices mostly. Sometimes we have to use 2 bytes, sometimes we have to use 4 bytes. So why don't we use this inside Java? Why don't we change Java to use only 1 byte for Latin 1 characters? And they really did it in JEP 254, which is called compact strings. So do you know JEPs? So JEPs are, I'm not sure, JDK enhancement proposals or Java enhancement proposals, and they are formulated, and there's a process to thumb up, thumb down, and this was thumb up, so they implemented it. And the JEPs are organized with some paragraphs, and 1 paragraph is a summary. And the summary of this JEP is adopt a more space-efficient internal representation for strings, namely 1 byte for simple characters. And there is also a heading goal. And the goal is to use this smaller representation, but preserving full compatibility for all related Java and native interfaces. So beside all the Java, all the string builder, string buffer APIs, there is also a Java native interface. If you're talking from Java to C, you have to use the Java native interface. So you have also to guarantee that all JNI programs still work after this string detail change. Okay, so I was at some Java 1, 10, 12 years ago, I don't know, where Charlie Hunt has a talk about this chap, and they told us that they get some client WebLogic core dumps, probably from the US and from European countries, and he belongs to Oracle. So, and the Oracle guys looked into the core dump and looked at the strings, and almost all the strings can be encoded with 1 byte because they are using English or German or Italy or something. So this is the reason why this chap was invented. And they did it, so till Java 9, the character value was coded like that, char value array. And in Java 9, they used a byte array. And they even reorganized the brackets. So it's the brackets belong to the type, and so the second writing is the Java writing, and the first writing is the C kind of writing. There is also a new additional field, which is called coda, which has two values, and these values identify is it a 1 byte coding or is it a 2 byte coding. So I'm a professor of computer science, namely software engineering. I think this is a masterpiece of software engineering. So eventually you have migrated Java 8 or older application to Java 9 or younger. And you will not have recognized some changes. Eventually, you have recognized that your program uses much less memory, because the strings are implemented with 2 bytes before, and now with 1 byte for character. So it's really nice. They are convinced that it works because they decided to do it as the default. So in 9, the compact strings were used. If you don't want to use it, you can switch it off with minus compact strings. But the default is it is on. Okay, second demo. It's also 3 or 4 tests, I don't know. 5 tests, but the 5th is not really important. Okay, so I have the German character A, English A, and there is some Unicode representation, and length is Unicode code units, as I told you, is 1. And there is also a Unicode a code point count. Code point and code unit are different things. This is also 1. And this one is a small reflection method programmed by me. It simply it returns the reference to the byte array. So the byte array contains one byte, only 1 byte. So I'm not sure what this character is, I guess it's from Czech, but I'm not from Czechoslovakia. I'm not sure. Slovakia. I'm not sure. And so the length is still 1. The Unicode code units they are using here is 1. The code point is also 1, but the byte array is using 2 bytes. So this is another character. I don't know how to pronounce it and what it is. And it's integer in Java is a 4-byte character, so it's an integer. So the Unicode code units used for this character is 2. The code point count is 1. And the number of bytes which are used is 4. So 3 examples, 3 characters, and 3 different encodings. 1 byte, 2 bytes, 4 bytes. Okay. Remember, the OpenJDK guides are really, really smart, but things can go wrong. In JDK 6, they tried another JEP, which is, it's not a JEP, it wasn't a JEP, but it was called compressed strings. It was, the concept was the same, use another character encoding, but they did it differently. So they have had 2 implementations for the class string. One with 1 byte per character and one with 2 or 4 bytes per character. And you have to turn it on via a JVM parameter, use compressed strings. It worked sometimes. Alexei Shipilev is an OpenJDK engineer, so it was employed by Oracle, and I don't know, 1 year or 2 years ago, he did a tweet that he joined AWS. So he's still an OpenJDK engineer, but employed at Amazon and still is implementing OpenJDK features. So and he said that compressed strings was an experimental feature, ultimately limited by design, error-prone, and hard to maintain. And this hard to maintain was the main problem. So he told us that it's a maintenance nightmare. So they stopped it, they revoked it with JDK 7, and in JDK 9 they did compact strings. Okay, next point, string deduplication in G1. It's the JEP 192, and the summary is, if there are strings which are not singleton strings, not intern strings, but strings on the heap, and there are equals, so they are using the same characters, the garbage collector should remove the one implementation or the one array, so that both array pointers point to the same array. So this is the idea. And to repeat, the G1 garbage collector should avoid wasting memory and reduce the memory footprint. So we don't have to do anything, but our programs will run faster because they are using less memory. Okay, I told you already that the strings are not interned, so string 1 and string 2. Interning means string 1 and string 2 point to the same string instance. Deduplication means, oops, sorry, it has some, needs some time to deliver. So string 1 and string 2 point not to the same string, but the byte arrays point to the same array. So this is before, and this is after. So they are not interned, but the arrays are deduplicated. So this was implemented in G1, as the chap has asked for. And sorry, and you have to turn it on. There is a parameter, JVM parameter, use string deduplication. And it's available since Java 8 update 20. Since Java 18, they also implemented in some other garbage collectors. Because if you know what to do, you can put it in the other garbage collectors too. So if you try to check what is garbage collected, there was a parameter, print string deduplication statistics, but this was removed in Java 9. And instead you have to use something more complicated parameter. I don't know why they did it, but it's like it is. Okay, demo time. Last demo for today. It's this one. And I print out the statistics. So I will not go into the details about the statistics, but I show you what I've done in my unit test. So you will remember that these are not constant expressions because they are using variables, though these concatenated strings are equals, of course, but they are, of course, not the same because they are instances on the heap. So, and also the byte arrays are not same. So the GC method is so it's a suggestion for the runtime. Please run the garbage collector, but you have no guarantee that it's called the garbage collector. So to be on the safe side, I have to use it 3 times. Sometimes it works also with 2, but not every time. So I'm using 3 GC calls here. And you also have to give the garbage collector the time to finish, because the garbage collector is running in a different thread. So, but if the garbage collector is finished, the strings are still not the same. They are not interned, but the byte arrays are same. So they are deduplicated. Okay. So there is a block entry, G1 from garbage collector waste to a collector, from garbage collector to waste management consultant. And what they did is they're using the Eclipse IDE and measured the less memory they're using after the garbage collection. And they told us that they are using 10% less memory. Heinz Karbutz, a well-known guy in the Java world, did also some measures, and he reports about 25%. Okay, so my last point for today, indify string concatenation. So my English is not very good. So if I read the JEP, I used my dict.leo.org. Eventually you will know it's a translator. And checked for indify, but I found nothing. So but I found after some Google search Wiktionary. And Java has changed the English language. We had a word which is only programming Java. It's only Java. Change a particular functionality to use invoke dynamic calls. So indify comes from invoke dynamic. Invoke dynamic, indify. So Java has changed the English language. Okay, so it's chapter 280, and it's a, I don't know how to say it in English and German, it's abgedreht. So the idea is, if you're using some framework, Hibernate 4.0 in an application, so it was compiled probably Java 5. The Java 5 compiler did some translation and generates some bytecode. And probably it was is bytecode string builder append. But if you run it on a JVM version 17, 18, 19, 20, eventually the JVM is capable of doing much quicker concatenation when she is allowed to do so. So the JVM is not allowed to do so if you use string builder append, punct, append, punct, append. So the idea is the compiler should generate bytecode that a later JVM version, a much later JVM version, can use more efficient to do the concatenation. And that's really abgedreht. Okay. So what they really did is they changed string builder append chains with invoke dynamic, it was introduced in Java 7. I don't know exactly, but I think Java 7 to do some invocations of other JVM languages. And invoke dynamic can use some bootstrap methods, and there is class java-lang invoke string concat factory. I will look into this class on the next slide. And you can convince yourself that this is true. So compile it with Java 5, and you will see string builder append. Compile it with Java 17, you will see string concat factory, I don't know, the method. So this class is public. So it's public API of JDK. So we can use it, but there is no use case to use it, because this class is only for the compiler. The compiler uses this class to generate bytecode of one method of this class. These methods are typically used as bootstrap methods for invoke dynamic call size to support the string concatenation feature of the Java programming language. It's only used to make it possible that a later JVM will use an invoke dynamic much more efficient than some older string builder append. And this is really crazy, I think. Okay, so I'm almost finished, but I will tell you that it will always go on. So probably I only have 45 minutes and I'm at the end in some seconds. But it's possible to talk another, let's say, half an hour, eventually an hour, only about string optimizations. For example, there was October 22, 1 year ago, and string hash code has a 6 times improvement, not 6%, but 6 times improvement for big strings, 10K strings, but 6 time improvements. Heinz Kabutz, I mentioned him some slides later, also measured string format with Java 16 and with Java 17. And string format in 17 is 3 times faster than in 16. So I promise it will go on, it will go on, it will go on. Okay, so I have told you something about intern strings. So please remember, string literals are singletons inside the JVM. There is something called compact strings, which means the representation of strings depends on what characters are inside the representation. String deduplication is a garbage collector feature, deduplicating the byte arrays, and identify string concatenation is some compiler hack to make it possible that some later JVM will execute string concatenation more efficient than using hard-coded string builder append chains. Okay, so if you want to download the code, you're welcome to download it, and eventually we have some time for questions.
Thank you very much, Bernd. Very interesting again.
Yeah.
Have still the need to enable the string deduplication as a JVM nowadays?
There is a JVM switch, so you have to turn it on.
You still have to turn it on.
Yes.
It's per default, it's disabled.
It's all, yes.
Oh, thank you.
Yeah. More questions?
Yeah, I wonder if you have an idea how much of the performance improvements of the JVM is just from strings?
From strings? I don't know.
But that sounds, there is a lot of potential.
Yeah. So if you think about strings, so I bet all of your applications, if you count the number of instances of every single type you're using, strings will win. You will have so much more string instances than any other data type. So think about web services, REST endpoints. So you deserialize and serialize unmarshalling JSON. So you build strings and build strings and build strings. And so if you want to optimize, strings are the type, the built-in JVM type, which is, of course, the best goal to optimize, because it will pay back. So they think about string optimization since Java 1.0. Okay, thank you very much.